Good evening, everyone. Now that it's 5 p.m. local time, we'll make a start on the lectures this evening. This evening, we're going to start, probably not finish, though. We'll start Unit 7. The topics in Unit 7 are derivatives, optimization, and basic ODEs. Some of you may have encountered these topics under another umbrella of a topic, and that topic is differential calculus. Some people might get a bit intimidated by the term calculus, and one of the things I hope to do this evening is not only convince you that you can all do calculus, but that this is an extremely important and very nice subject that allows us to deal with lots of different things that occur in the real world. Some of you may have already come across the idea of calculus and some of the things we treat in calculus. And so certainly we'll get to some of those things later on. We'll give nice rigorous definitions of everything. But I want to spend a bit of time to start off with giving you some intuition about what differential calculus is all about and why we would need it. So the name of the game in differential calculus is a discussion of these things called derivatives. Now, what is a derivative? A derivative, more or less, is just an instantaneous rate of change. So before I get on, I see we've got a question already. Would we cover PDEs in this course? We cover some ODEs towards the end of this unit. I do not believe we'll be covering PDEs in any serious way in this particular course. I think that's a bit of a shame perhaps, but perhaps there'll be other opportunities to discuss PDEs later on, or maybe you might have to take different courses. We'll see how we go. Okay, derivatives, instantaneous rate of change. So really the question we should have in the back of our minds is as follows. If you've got some quantity that's changing with time, measured in some units, doesn't really matter. Let's say you've got a graph of it. The question we want to ask ourselves is, how can we describe how quickly this quantity is changing? Now, if you happen to be at this particular time here, how would we measure how quickly the quantity is changing here? Well, perhaps the natural thing to do is go backwards in time a bit and measure how much the quantity has changed between this point and this point. So this gives us an average rate of change. It tells us that in the last minute, for example, the quantity has changed by a certain amount. Now, the problem with such an approach is that even though it could be true what you just said, that the average rate of change is a particular amount, it might not be giving you all the information you might need or want. For example, in this particular graph I've drawn here, at this particular time here, it seems that the quantity is growing a lot quicker than we would have really been able to account for if all we were paying attention to was the difference of the quantity between these two times. You might be able to make it a bit better by, instead of going all the way back here, going back here instead, looking at the rate of change between these particular points. Calculus is all about what happens when you push this idea to its natural limits. When we do that, what we end up with is a rate of change which is instantaneously accurate. It's not an average that could be changing immediately. It gives us a true understanding of exactly how fast a quantity is changing at that particular point. Now, why do we care about these things? Well, from a philosophical perspective, from a mathematician's perspective, basically we want a way to rigorously quantify changes that occur in real life. Mathematicians see that lots of quantities in real life are changing, and they want clear and concise ways of describing how those things change at any given moment. Maybe you are unconvinced by that, so now I want to give you what I think is a fairly good example of the need to talk about instantaneous rates of change. The example I'm thinking of is perhaps the obvious one. When I thought of situations in real life where we're always looking at instantaneous rates of change, my mind went to the speedometer on a car. So as we're driving, the idea is this: the speedometer is meant to be giving our instantaneous speed at any given point. It's not measuring our average speed over the last minute, for example. It is endeavoring to give us a precise description of how quickly we're traveling at that precise moment. So my question for you, and this is something I would actually like some participation in, my question is, why is it important that a speedometer gives you your instantaneous speed rather than, for example, the average speed you've traveled over the last minute? So if you were interested, I wondered if you could please answer this question for me, giving a brief sentence answer in the chat. While you're answering that, one obvious, yes, you beat me to it. One of the responses we've had so far is that, well, what I think the response here is that the speed limits is needed because, well, on a particular road, we're told that our instantaneous speed of travel cannot exceed a particular amount. So at least in Brisbane, if you're driving around really suburban areas, the default speed limit is 50 kilometers per hour. So let me try and refine the question then. Why does the government insist that at any given point in our travel, our instantaneous speed is not exceeding a particular amount? Why do they insist on instantaneous speed limits instead of, for example, average speed over a particular journey? Why is it so important that instantaneous speeds are mandated? Any ideas on that? Safety. Yes, good one, Shripad. I wondered if you could elaborate on that just a tiny bit. Yes, that's more or less exactly what I'm looking for there. So I'm going to push this to its extreme. Why is it all about safety? Well, if you're in the unfortunate situation that you are in a car crash, I would suggest that the thing that determines just how much damage is done to you, your passengers, and your car, it more or less all comes down to how quickly you're traveling, as well as how quickly anyone else is traveling who is crashing into you. At the moment of crash, you don't really care how slow or fast you are traveling in the last minutes. You only care about how quickly you are traveling at the precise moment of impact. That number there, whatever it is, I suggest is going to be one of the most important measures of how much damage is going to be inflicted on that in that crash. So this I perceive to be a really important reason why we would be interested in mandating the study of calculus, because it comes down to speeds. Okay, so I hope I've convinced at least some of you of the importance to look at calculus, and in particular the derivative. Now we'll start to make a bit of a move towards trying to rigorously describe what the derivative is and how you define it. As I've discussed, the derivative is all about the instantaneous rate of change. If you're looking at a function that has a graph, the instantaneous rate of change is meant to be this slope. The slope of a tangent line that lies on a particular point of the graph of f. So for example, if we've got a function and we're graphing that function, and we pick a particular point A on that graph, then the instantaneous rate of change, what that is it's the slope of a line that lies exactly tangent to this particular line here. I know this particular line I've just drawn isn't very straight, but hopefully you get the idea there. So the line itself is not the derivative. Instead, it's the slope of this line that is the derivative. Well, okay, fine. But how do we actually go about finding the slope of that line? So I've got a comment from KC that's moving towards where we're really going here. Can we consider a derivative to be a change in y for an infinitesimal change in x? Yes, I would suggest that's exactly what the derivative is. The only problem I can see with your definition is we haven't really made sense of what an infinitesimal change means yet. So very soon we'll make sense of what such an infinitesimal change means, and giving credit to your definition there. So we've got, the idea is we want to find this slope. How can we find this slope? In principle, if you're just given a function, it might be pretty hard to work out straight off the bat what this particular slope is. So instead, what we do is pick another point on the graph. Let's say we've got this function here. We're trying to find this particular tangent line here. So instead, what we do is look at these 2 points here, the graph of the function at the point A and the graph of the function at the point B. The idea is that the tangent line at A should be, oh my goodness. The tangent line should be close to the line that's found by joining the dots between these two particular points here. Excuse me, I just need to close this window. Yes, so this particular straight line here should be an approximation. Hopefully it should be an approximation to the tangent line here. Well, the way I've drawn it, that's not particularly good, but the thought is perhaps that we can do this a bit better by moving the point B closer and closer to the point A. So before we start moving things close, before we start moving the point B close to the point A, let's just work out how we can actually evaluate the slope between B and A. Well, this is just your standard rise over run formula. If you're looking for the straight line that joins F, the point B, F, if you're looking for the slope of the straight line that joins the point B, FB to the point A, FA, well, this is a straight line and its slope is determined entirely by the rise over run formula. We've risen, the distance that we've risen up here, well, we've gone from FA to FB. So this is the rise. And the amount we've traveled in the x direction is B minus A. So this is the rise over run formula. It might be helpful to notice that there's another way of formulating this. If you write B equals A plus H, where H is just some number, then of course F of B is the same as F of A plus H, and B minus A is exactly equal to H. And so our formula can alternatively be written as F of A plus H minus F of A divided by H. So as I suggested before, this slope that we're finding here is not going to be exactly the slope of the tangent line that we're actually after. But heuristically, we would expect that this formula does a good job, especially if B is close to A. Equivalently, if H is small. So this is really the idea behind the derivative. We're going to be taking limits, which is why, of course, we started looking at limits last time, or maybe it was the time before. We're now in a position to take the derivative. I guess before we do that, maybe a better version of the picture I was trying to draw. We've got this graph f of x and 2 points. We're trying to find the slope at the point at the point A. The idea is that this slope should be quite close to the slope of the straight line joining the graph from A to B. All right, the definition of the derivative. Let's say you have a particular function defined at a point A. Then the derivative of the function f at this point A is defined to be the limit as h approaches 0 of the slope that we were describing before. So we pick a point close to A, we look at the slope of the corresponding graph of the function, and we move the points closer to each other, and we'll see what we end up with. Now, before we get too far into it, just a slight technicality I need to alert you of. We really need to insist that the derivative is a real number. We talked briefly in previous sessions. We talked briefly about what it means for a limit to be equal to plus or minus infinity. If it so happens that this limit is plus or minus infinity, we still say that the derivative does not exist, even though the limit exists in some sense. So for the derivative to exist, we need the derivative really to be a real number. Right. So why do I need to insist on that? What would that even look like? Well, let's say we've got a graph of a function f of x, and let's say that our point of interest is A. And let's say that as we're traveling along, at the point A, we hit this sort of vertical tangent here. In some sense, you could say that, you know, the tangent line here is this straight line here. And so the derivative is infinity. That's something we don't really like to talk about in mathematics. If you end up with a vertical tangent, that means that the function is not differentiable, even though the tangent line exists, because we'd have to say that the slope is infinity, and we don't really like to do that. Right, now that we know what it means to have a derivative exist, if the derivative does exist, we say that the function f is differentiable at the point A. If the derivative does not exist at that point, we say that the function is not differentiable at that point A. So this is differentiability at a point. The next natural thing to talk about is differentiability on entire intervals. So let's say we've got a function defined on an open interval. Let's say that interval is A up to B. Then if it so happens that f is differentiable at every point inside that interval, we'll say that the function is differentiable on that entire interval. Now, just some notation. We've used the f dash of A notation. This is typically what's called a Newtonian notation. So this is where derivatives are denoted with dashes. But we also have this notation here. This is known as Leibnitz notation. And this is where the derivative is defined to be df on dx. So this is where we get we start thinking about infinitesimal variations here. This df on dx is meant to look like delta f divided by delta x. This is basically just the rise over run formula. A small change in f divided by a small change in x. We take a limit. This is what makes it an infinitesimal change here. And this goes, as we take limits, this goes to df on dx. So this is saying the exact same thing. It's just a different notation. Now, one important thing to note is that even though we look at derivatives at a single point, we can let that point vary, which means that the derivative of a function can again be another function, at least on an appropriate domain of definition. Okay. So we've seen the definition of derivative. We've seen notation. Let's have a look at an example. Where does the derivative come in handy in terms of actually solving questions? Okay, so this question, we've got a function f of x. It's defined to be x squared plus x. Something to note perhaps is that the domain of f, this is the set of all real numbers. If I put any real number in there, then I get something, then the function is defined there. And so the domain of f is all of the real numbers. This question is asking us to calculate the derivative. And moreover, well, we need to use the definition of a derivative. I suspect many of you will know how to differentiate this because you would have seen it before, but we're not going to use any of our knowledge, any of our previous knowledge to do it. We're just going to use the definition of the derivative. So how does this go down? Well, remember, we're only using the definition of the derivative. The derivative, if we pick any point x, the derivative of this function is defined to be this expression here. We take a change in f divided by a change in x, and we take the limit as that change goes to 0. In this case, h is the number that describes how much we're changing, and we're going to send that to 0. Okay, how do we do this? Well, note, we know exactly what f looks like here. So we know what f of x is. It's equal to x squared plus x. And of course, we also therefore know what f of x plus h is. So maybe let's take this rather slowly. The function f takes as input a number. The output is that number plus the square of that same number. So that means f of x equals x squared plus x, whereas f of x plus h, that's that number plus the square of that same number. So this is what f of x plus h is. So that goes there, and this goes over here. Great. Well, now we're going to expand the brackets and hopefully we'll simplify. So of course, remember that x plus h squared, that's the same as x squared plus 2xh plus h squared. The x plus h has just gone down here, and the minus x squared plus x becomes minus x squared minus x. What you may notice is that we get a fair amount of cancellation here. This term cancels with that one, and this term cancels with that term there. What we're left with is 2xh plus h squared plus h divided by h, and we're trying to take the limit of that expression as h tends to 0. Okay, well, let's simplify this. Let's take this over here. 2xh plus h squared plus h divided by h. This is equal to 2x plus h plus 1, at least if h is not equal to 0. Remember, we're dealing with limits here. Limits only care about the expression when h is really small. It doesn't care about what it is when h equals 0. In this particular instance, we find that this expression is not even defined. This expression isn't even defined for h equals 0. But that doesn't matter because we're taking limits here. So since h is not equal to 0, I'm allowed to do all the cancellations down here. And remember, I'm taking a limit as h goes to 0. H doesn't actually appear here or here. So that just pops straight out of the limit. Whereas this term goes to 0 since h is going to 0. So that means that for each x, the derivative is 2x plus 1. Note that no matter what x is, the limit always exists. So that means the derivative always exists, which means that f is differentiable for every real number, and the derivative is given by this. The derivative at any point x is equal to 2x plus 1. I hope that was all straightforward. Please speak up if you think anything was particularly unclear, or if you would like further explanation of anything here. I'll just give it a brief pause there. All right, thanks, Elwan. I'll assume you're speaking for the whole class there. Right, moving on. That was a nice example. We'll now turn to a slightly more tricky example. Before we get into that, I'll answer another question there, which was a question about the derivative rules. A little rusty. Yes, we will certainly be going through the derivative rules. I'm assuming you mean things like the product rule, the quotient rule, and the chain rule. Yes, those are all important, and we'll get onto those in due course. Okay. Now we've got a function f of x equals e to the power of x. Calculate the derivative. Okay, so this is a bit of a tricky one if you don't know what to do. So definition, the limit, remember the definition of the derivative is f of x plus h minus f of x divided by h. We're taking the limit as h goes to 0. Just use the definition of the function, e to the power of x plus h, because f of x plus h equals e to the x plus h, minus e to the x. What's going on here is I'm using the index rules. That's interesting. What's really nice about this is that since we're taking a limit in h, we more or less treat x as a constant here. And so that means that we can take this constant out the front, and we're just left with this particular limit here. But you may notice something. This limit is one we actually already covered in a previous lesson. The limit of e to the h minus 1 on h is equal to 1. So as was suggested in the comments, the limit of this particular function, this particular limit is equal to e to the power of x. So as was suggested in the comments, the derivative of f is equal to f. So this is particularly interesting. Now, for me at least, this raises the question of where does this particular limit come from? How do we know that? Well, it's a bit tricky. I could discuss it with people in office hours if they were interested. It's a bit tricky, but also I like to think of this another way. Even though that this computation does work, I would like to point out that if I were asked to define the exponential function, I would do it this way. E to the x, the function f of x, which is given by e to the x, this is the unique function so that, well, what are the really nice properties of this function? Well, as was suggested in the comments, it's the function that satisfies f prime of x equals f of x, and f of 0 is equal to 1. So even though you can define the exponential function to be, well, you define the number e and then raise that to the power of x, and that's your function, my preferred way of defining the exponential function is to say that it's the unique function that's differentiable everywhere, whose derivative is exactly the same as the function itself, and which starts at 1. Now, why do I bring this up? Well, this is this way of defining functions. It's quite similar to a question I snuck onto the homework assignment. So in this particular way, you can see that the exponential function is defined to be a unique solution of a differential equation. We'll talk about differential equations a bit later. And in your homework assignment, I gave you another collection of functions that were defined to be the unique solutions of a particular equation. I liked that question. I hope you enjoy doing that as well. Maybe you won't. Right. Now, yes, moving, before we move on, just summarizing this particular question here. the conclusion of what we've just done is that f is differentiable everywhere, and the derivative of f is the same as e to the x. What is particularly useful about derivatives from a data science perspective, or at least from the perspective of this course, is that Mathematica can do your derivatives for you. Now, there are a few different ways of computing the derivative with Mathematica. So I did a couple of these ways for you. So what's going on here? Let's work from top to bottom. Let's see what's going on here. Well, the function I'm trying to differentiate here is obviously x squared plus x cubed. So how am I doing that? Well, in Mathematica, what you can do is take a d, square brackets, open square brackets, you put the function, and then you've got to specify what you're differentiating with respect to. Because in Mathematica, it's very easy to include additional parameters, additional constants. You need to tell Mathematica what variable you would like to differentiate this expression with respect to. So this particular quantity here, this is exactly equal to the derivative, shouldn't be doing that. The derivative of x squared plus x cubed, and we're taking the derivative with respect to x. So this is a Leibniz. This is essentially a Leibniz version. The notation that this particular Mathematica input is closest to Leibniz notation. Of course, Mathematica can compute it for you. It's equal to that. So that's a simple way of doing it. We've got someone unmuted, I think, was making a bit of noise. I'm just going to go ahead and mute you if you don't mind. All right. Now that's one way of doing it. You just shove everything in and make it compute it. But sometimes the functions you're dealing with might be particularly long. So it might be expedient to define the function first in its own line. So this is how you would define a function with Mathematica. And then you would tell Mathematica to differentiate that function with respect to the variable x. So the output of this particular result doesn't seem to, oh, wait a second. Oh, I see. Being a bit tricky here, this output is actually corresponding to this line, whereas this output is corresponding to this line. Since I didn't make it compute anything between writing this and this, it gave me both of them when I did control, what is it, control shift, I think. Okay, well, that's another way of doing it is using the classical Newtonian notation. If you've already defined your function, then all you need to do is put a dash in there, and it'll tell you what the answer is. So that's quite nice. We've got a comment here. It is the function itself. Zhao Wang, were you talking about the exponential function before? Yes, awesome. Thank you. That's Mathematica and derivatives. Now I've given you the definition of the derivative. We've looked at some examples. Now we're going to start really trying to build up the theory of derivatives by looking at some well-known examples of derivatives that would be very good for you to know, as well as the derivative rules that we'll be talking about later. First of all, some useful derivatives. First, and perhaps most obviously, if you've got a function that's a constant, so let's say that your function is f of x equals c, where c is just some constant, doesn't depend on x, then the derivative is obviously 0, because derivatives are meant to be measuring how much something is changing, and if it's not changing, that means it should be 0. You can see this rigorously, of course, by looking at the expression that actually defines the derivative. Remember, the derivative is defined to be the limit as h approaches 0 of change in f divided by change in x. But if f of x is equal to c for all x, then f of x plus h is also equal to c for all x, same as f of x. And this is just equal to the limit as h approaches 0 of 0, which naturally is going to be 0. So this is just a cute way of saying that constants don't change. That's almost a tautology there, but anyway. Next important one, if you're looking at the function f of x, which is equal to x, then the derivative is 1. Of course, that's because the slope of that function is equal to 1 everywhere. Of course, you can see it more rigorously by checking, by actually working out the definition of the derivative. Limits of f of x plus h minus f of x divided by h. That's equal to the limit as h approaches 0. Now remember, f of x is x, so f of x plus h is equal to x plus h minus x divided by x. Now what's quite nice here is that the x's cancel. You're left with h divided by h, and that's equal to 1. No real surprises here so far. This one is a little tricky. It's surprisingly difficult to prove, but nevertheless, it's something that you can use. Well, I recall that in the assignments, you're meant to do some of these things without using this particular rule, but I'll give this rule to you now for the moment. If you have a function which is equal to x to the power of some alpha, then the derivative of that is found by putting that alpha out the front, and you go x to the power of not alpha this time, but alpha minus 1. So really what happens is this alpha goes, if you're differentiating this alpha goes there, and this whole expression goes over here, but you've got to subtract 1 from that. This holds quite generally, but you really have to be careful with where this thing is defined, because this is a course that deals with real functions. We're not really dealing with complex functions here. So that means we're not really allowed to look at expressions like this. We're not allowed to raise a number to the power of something that's not an integer. So for example, we're not allowed to raise minus 1 to the power of a half. If you've done complex numbers before, you'll know that this is what we call the imaginary number I, but we're not really dealing with this in this course. Maybe that makes you a bit sad, it makes me a bit sad, but mostly what we need to deal with is looking, in order to make this expression make sense in this course, really what we need to insist on is that either x is positive, or if x is negative, we need to make sure that alpha is a whole number. Okay, so that aside, we've got the sine and cosine functions. They have this really nice duality here. The derivative of the sine function is cosine. On the other hand, the derivative of cosine is minus sine. Now, if you don't know these already, I would say it would be very useful to learn this, in particular, where the minus sign goes. It is very important the line goes there and not here. Because if you don't get that right, you completely change the definition of sine and cosine. These would definitely be good ones to learn. So far, we've only been taking one derivative, but there's nothing really stopping us from going further. In particular, for example, let's say we've got a function, we've found its derivative, which we call f. Then second derivative of f, which is denoted f prime. Oh, I see that. Oh, sorry, it looks like my iPad was lagging behind a bit. I think it's okay. The second derivative of f, that's just defined to be the derivative of f prime. So you can do this over and over again. And if you take n derivatives, the resulting function is called the nth derivative of f. And you typically denote that with f, with this notation here, f subscript n in brackets, and then your x. This is Newtonian notation. But there is a Leibniz equivalence of this. And this is this interesting expression here. Now, there is a reason why the n's go here and here, but I won't get into that. This is just a convention. What's an example? Well, if the derivative of sine is cosine, then the second derivative of sine is whatever the derivative of cosine is, which in this case is minus sine of x. So that's interesting. The second derivative of sine is minus itself. Now, second and first derivatives come into play a lot, especially in physics, because if you're using a function f of t to describe the displacement of an object at time t, so how far it's traveled, where it is, then the first derivative is defined to be the object's velocity, how quickly it's moving. And the second derivative is its acceleration, how quickly its speed is changing, how quickly its velocity is changing. So you will have seen these things before, perhaps. Before going into more rules for differentiation, I'd like to take another Mathematica pause here. Mathematica can deal with higher order derivatives as well. How do they go down? Same thing as before, except so you take the d here to indicate that you're taking a derivative, x cubed, the function that you want to differentiate, but this time, instead of just specifying what variable you're differentiating with respect to, you need to specify a pair, namely the function that you're wanting to differentiate with respect to, and how many times you're wanting to differentiate with respect to that particular function. So if you look, what this is saying is that if you look at f of x, which is equal to x cubed, Mathematica is telling you that the second derivative is equal to 6x. So we can see that because, well, we know our derivative rule that f prime of x, using the rule that the power goes down the front, and we're left with x to the same power minus 1, that's equal to 3x squared. When we differentiate again, we get back here. What's really interesting is that sometimes you can actually leave the number of times you're differentiating as arbitrary. So this time, I'm wanting to differentiate a function, which is again, f of x equals x cubed. I want to differentiate with respect to x, but this time I'm not going to specify an actual number that indicates how many times I need to differentiate. This time, I'm just going to let that number be n. Let's see what Mathematica spits out. Well, it gives us x to the power of 3 minus n times this thing here, factorial power of 3n. So what does this mean? Well, I hadn't actually really come across this function, the factorial power, before until doing this particular, until I prepared for this particular class. I think what this means is you take 3 times 2 and you just keep going down in integers until you've done this n times. Now, of course, if n is bigger than 4, you're going to include a 0 here. And as soon as you're multiplying by 0, that cancels out. That's indicating that if you take the fourth derivative or higher of the function x cubed, you're just going to end up with 0. We can make this even more funky. Let's include another random number here. Instead of differentiating the function x cubed, I'm going to differentiate the function x to the power of k, where k is some number. I'm differentiating with respect to x, not k, and I'm differentiating n times. This time what I end up with is x to the power of k minus n times this factorial power function before. Now remember, sometimes you might be wanting to differentiate functions that get really, really big. So in that case, it might be helpful to define the function by itself and then indicate that you're differentiating that function n times with respect to x. So this is the output of that, and this is the output of that. I hope that's clear. You might want to try this out yourself at some point and have lots of fun with Mathematica differentiation. Now we'll get into the rules for differentiation that are quite useful. So to set the stage here, we're going to take two functions, f and g, which are both differentiable. And we're going to let c be just some constant. Then a number of rules that we'll need to keep track of. I suggest to you that a lot of these rules are in fact quite natural, but in any case, they would be rules that you should learn. The first one is pretty easy. If you take the function f and multiply it by a constant c, then the derivative of that new function is the same as that same constant c times the derivative of the old function. Perhaps that's not too surprising. Another one that I think isn't really all that surprising is this one here. If you take two sums and add them together and take the derivative, then that's the same as the sum of the individual derivatives. The same works for subtraction as well. So in words, how do you describe this rule? The derivative of a sum is the sum of the derivatives. These two rules combined imply that the derivative is a linear operator. I won't spend any time explaining what that means, but if you've come across the word linear operator before, linear matrix, you might know what this means. Derivative is a linear function. I won't say function, I'll say operator. So these are known as the linearity rules for derivatives. Well, what comes next? Now things start to get a little surprising, perhaps. The products. This is called the product rule here. Now, unlike addition, it is not true. It is not true that the derivative of a product it is not true that the derivative of a product is the product of the derivatives. So this is not true. If this is in your head, you need to get it out of your head right now, because it will lead to heartache and misery if you try to use this rule in assignments or exams. Instead, because the rule for the derivative of a product is so tricky, it's actually given its own name. It's called the Leibniz rule for derivatives. And what it's saying is as follows. If you take a product and take its derivative, then that's the same as the derivative of the first function times just the second one, plus the first function times the derivative of the second. There is some intuition behind this. Actually, maybe I can finish off with that. The reason that this particular rule is true has to do with, well, it has to do with, you can prove this rule just using the definition of the derivative, but perhaps a much more intuitive way of describing what's going on here is by thinking about f and g as describing the lengths of a particular rectangle. Then the product fg is describing the area of this rectangle. What happens, let's say that f and g are both time dependent. So let's say that as f is moving, it's heading off in this direction here. Let's say that as g is moving, it's heading off in this direction here. Then after a small amount of time, the extra area we've come across here can more or less be described by this and this. Now, of course, there's also this area here, but we sort of think of that as negligible. Then if f and g are changing, the amount that the area is changing by is this bit here, let's call it 1, and this bit here, which is 2. Now, the area of 1 plus the area of 2, well, what's the area of 1? This is equal to f times a small variation, a small variation in g, which we can think of as g prime, plus this area 2, which is equal to a small change in f prime times g. So this is very abusive notation here, but this is more or less the intuition behind where this product rule comes from. So it's 5:51 now. I'll give us a 10-minute break. If you have any questions about this, please feel free to put them in the chat. Yep, have a good break. I'll see you in about 10 minutes. Hello again, everyone. Before we proceed with rules for differentiation, I need to apologize as this intuition for area that I gave you was slightly off. It was missing something. The idea is that as f is changing, the amount that this is changing by is not f prime, but rather is f prime multiplied by however much you're changing t by, or at least it's approximately that. And same thing over here. This extra heights that we're getting is not g prime, rather it's approximately g prime times the amount of time we're changing by. And so that means we've got changes of time both here and here, but it's when we divide by delta t and take the limit that we get the product rule. So that's an area interpretation of the Leibniz rule. As I suggested, you can actually prove this quite rigorously using just the first principles definition of the derivative. If that's still unclear, I'm happy to spend a bit more time talking about it if you would like. Please let me know if that's the case. Now, the next rule. The next rule is the quotient rule. So this is another funky one, even more funky than the product rule to some extent. So the quotient rule for differentiation, this is what happens when you take a function f divided by a function g, and you want to take the derivative of the resulting quotient function. Now, the derivative of this is quite involved. So if f is on top and g is on bottom, then on the top of the derivative, we've got f prime times g minus g prime times f. It is very important, the order in which you do this. There's a plus sign in front of the term that differentiates the top, and there's a minus sign in front of the term that differentiates the bottom. It's very important that you get that the right way around. Of course, it doesn't matter. You could use f, g, u, v, any other functions you want, but it is important that this order is done correctly. And then on the bottom, you've got g squared. Now, it would be worth mentioning that you can only use this quotient rule if the denominator is non-zero. Because if the denominator is equal to 0, then not only is this f divided by g function not defined, but its derivative is not defined either. So we've got a comment/question here. F divided by g can be denoted as f times g to the power of -1. Yes, and you actually touch on a very interesting point here that it would be worth mentioning. The reason I haven't done that here is because when you include that to the power of -1 term, that things can get a bit confusing. So it is very confusing in mathematics that we can use this to mean the inverse function, but we use g of x inverse to be the one divided by g of x thing. These things are not always equal to the same thing. And so to answer your question, yes, in this case, you would write f of x divided by g of x is the same as f of x times g of x to the power of -1. If you don't use the x notation here, it can get a bit confusing. And that is something that is one of the most unfortunate things notation-wise in this course, that this to the power of -1 can mean both inverse in the sense of functions as well as inverse in the sense of real numbers. Okay, so that was the quotient rule. Now, you may notice that all these derivatives I've given you have been phrased in terms of the Newtonian formation of the derivative. You are allowed to write all of these rules using Leibniz notation, and these are described as follows. So remember, Leibniz notation is d of function divided by d of whatever the variable is. So if your function is f multiplied by a constant, then d of that is c times d of the original thing. Similarly, the addition subtraction rules look like this. The Leibniz rule in Leibniz notation looks like that. And the quotient rule looks like that. Now, Kai has another interesting question about this FG inverse question. The point was we can think of f divided by g as f times g to the power of -1 and then apply the product rule. My answer to that is yes and no. The reason I say that, well, yes, it is true because, you know, if f divided by g is equal to f times g to the inverse, you should just be able to apply the product rule to that to find the quotient rule. Now, the reason we can't do that yet is that in order to do this, in order to use the product rule, well, what is the product rule? It's f prime times this plus the derivative of the second term times f. Now, the biggest problem here is how do we evaluate that? Now, while it can be done, the reason I didn't include it here is because in order to use that, you need the chain rule for differentiation that we haven't actually covered yet. But yes, as soon as we cover the chain rule, yes, you can actually recover the quotient rule using the product rules and the chain rule. Yes, of course, the answer is g to the power of -2, but you've got to multiply by the derivative of g again. So that's the chain rule. So that's, we'll get to that shortly. Let's have a look at the use of these rules to calculate derivatives that we all like. One of these functions is the tangent function. So remember, you might recall that the tangent function with input x is defined to be the quotient of sine of x with cosine of x. Now, what we're asked to do now is actually calculate the derivative of this function tangent of x. Sorry, I need to close my window again. The dog started, neighboring dog has started barking again. Okay, so we were trying to find the derivative of the tangent function. Tangent is defined to be sine divided by cosine. So since we know how to differentiate both sine and cosine, in principle, that means that we should be able to use the quotient rule to find the derivative of the tangent function. And indeed, that is the case. Before we get going with that, though, we need to note a subtlety, namely that the quotient rule only works if the denominator is non-zero. So at our point of differentiation, we need to insist that the denominator is non-zero. Well, if we're looking at the cosine function, then that is 0 whenever x is equal to pi times some integer plus a half. But apart from those points, cosine is non-zero. So that means that we can use the quotient rule to find the derivative everywhere except for these points here. Okay, let's say we're at a point that's not any of those. The quotient rule. Now, remember the quotient rule, it's important that you get the order right. It's more or less like the product rule, where you take derivative with a non-derivative plus a derivative plus the non-derivative of the other thing. But it's important that because, well, we've got a plus and a minus here, the plus goes with the term that differentiates the top, and the minus goes with the term that differentiates the bottom. So we've got a question here, more or less asking whether noting points that we have to exclude from our domain in order to take the derivative. Yes, I would say it's good practice and probably important that when you're doing this sort of thing in an assignment or exam, that you do mention the points where the derivative does not exist. Okay, so we've got the derivative of sine times cosine minus the derivative of cosine times sine. Now remember, the derivative of sine is equal to cosine, So that means that this term just becomes cosine squared. On the other hand, the derivative of cosine is minus sine. Those two minus signs cancel out, and we get cosine squared plus sine squared. You might remember that a fundamental trigonometry identity which says that cosine squared plus sine squared is always equal to 1, no matter what your input is. So that means we end up with 1 divided by cosine squared here. This is probably a good enough place to stop. The answer is 1 divided by cosine of x squared. But we also may notice that, well, by definition, 1 divided by cosine is defined to be this sec function. And so that means that the derivative of tan can also be thought of as the sec squared function. So that was an application of the quotient rule. Remember, we have to keep in mind that we have to stay away from dividing by 0 problems. Now, the last important rule for differentiation that we'll cover is one that we actually already got greedy and talked about early, the chain rule. Now, why is it called the chain rule? It's because we're looking at functions that are composition functions, so are expressed as chains of other functions. I've got a function, f of x, which is given by g of h of x, where g and h are both their own functions. Let's suppose that g and h are differentiable. Then what do we get? Then the composition function, this chain function, is also differentiable. And we have this particular rule here. The derivative of this composition function at a point x is the same as the derivative of the outer function evaluated at the inner function of x multiplied by the derivative of the inner function of x. Now, you may think that this all looks like a bit of a mess, and it is an unfortunate consequence of Newtonian notation that these things often look like a mess, but there is a Leibniz formulation of the chain rule as well. This is something that people like to look at because it's much more aesthetically pleasing. If you just, for the sake of computation, you let this function h of x be equal to u, and you let y equal f of x, then this is equal to g of h of x. But if we're calling h of x u, then this is just gu. And then the Leibniz formulation of the chain rule looks like this. The derivative of the original function equals the derivative of the outer function divided with respect to u here, and then du on dx. I wanted to actually take a bit of a pause here and ask you a question. I think I know what your answers will be. My question is, do you prefer the Newtonian formation or the Leibniz formation of derivatives? Which one do you like? And if you like a particular one more than another, could you explain why? Okay, so I've got a first one because Leibniz sometimes will confuse the letter. Newton. Okay. I was actually assuming that all of you would prefer Leibniz because it's much more intuitively clear, but we've got a good mix here, which I'm very pleased to see. So let me explain to you what my position on this is. When I was learning calculus, I really enjoyed the Leibniz notation because, well, it was very intuitively clear what all of the, expressing things in terms of dy on dx and dy on du, that clearly coincides with changes in y divided by changes in u. So from that perspective, it was much more intuitive and aesthetically pleasing. But as I grew up, even though this looks quite nice, I found that I really had to use this notation. And the reason is there are no ambiguities with this notation, even though it looks a bit uglier. What do I mean by that? Well, when you take derivatives, you're differentiating a function. There's no reference to the inputs. And so that means you can actually express this without reference to the x here, which makes sense because you shouldn't need to reference the input variable when you're taking derivatives. But with this notation, you're sort of forced to use variables that might not really make much sense. And in particular, when you're using the chain rule, I find it's very easy to make mistakes with this notation. Especially when you're playing with the chain rule, because when you're playing with the chain rule, you've got all of these variables flying around and it's hard to keep track of, how all of these relates to each other. And so even though I would suggest it'd be a good idea to get comfortable with both, Leibniz notation, because it makes the underlying intuition quite clear. But ultimately, I think that I will declare that Newtonian notation is the correct way to think of derivatives and the chain rule. Both are accepted in quiz and assignments, right? Yes, I would expect that would be the case. But if if you're going to use Leibniz, make sure that all of your variables and functions are quite clear and that you don't make any mistakes with notation. Right. Okay, so I've looked at the chain rule. Let's have a look at an application of the chain rule. Question. Let y equal the square root of sine x. Calculate dy on dx. So interestingly enough, in this particular question, the Leibniz notation is actually forced upon us. Notation. If we were to do this using the Newtonian formation, we would have to say, let f of x be equal to the square root of sine of x. And then the question would say, calculate f prime of x. That aside, as I said, the Leibniz notation has been forced upon us here, so let's just roll with that. Okay. Let's introduce extra variables. Let's define u to be sine of x so that y is actually given by the square root of u. Okay, well, what we're being asked to calculate is the derivative of y with respect to x. Okay, let's do that. The Leibniz version of the chain rule will tell us that the dy on dx is equal to dy on du times du on dx. Now, since y is equal to the square root of u, we can use that power rule for derivatives we had, because remember, u is the same. The square root of u can be thought of as u to the power of a half. So that means the derivative of this, the half gets pulled out the front, and we go u to the power of a half, but then we've got to subtract 1. So this is equal to a half times u to the power of minus a half, which is precisely equal to this guy here. 1 divided by 2 times the square root of u, because u to the power of minus a half is the same as 1 divided by the square root of u. Okay, great. Now that we've done that, we've got to put everything in terms of x again. Remember, u is equal to sine of x. So 1 divided by 2 times the square root of u is 1 divided by 2 times the square root of sine of x. And du on dx, well, u is sine of x, and the derivative of that is just going to be cosine of x. Now, we've got another interesting question here. If a question is given in if a question is phrased in terms of Leibniz notation, can I use another notation to answer? I'd say that unless it specifically says use Leibniz notation, and I can't imagine any question would ever do that, then yes, you should feel free to answer it however way you want. I mean, I guess in this particular context, it'd be preferable to keep it in Leibniz notation because that minimizes the risk of you getting confused about what the question is actually asking. But I guess if you're absolutely confident that you know what the question is asking and what the equivalent Newtonian formation of that is, then you should feel free to do it. As I said, I would, if I were writing questions, I would tend to put everything in terms of Newtonian, the Newtonian formation. Okay, thanks for your question. Right, so this derivative here, we've actually computed the derivative now, but there is another subtlety here. We need to insist that sine of x is strictly bigger than 0. Why do we need to do that? Well, I mean, we're taking the square root of something. We need to, first of all, we need to insist that what we're taking the square root of is non-negative, because you can't take the square root of a negative number. But it turns out that being non-negative is not enough. We actually have to be strictly positive because we're dividing by the square root of sine of x now. We don't allow that to be 0. If sine of x is 0, then that is a point where the function does not have a derivative. Hope that's clear. Now, continuing on with this eternal struggle between Newtonian and Leibniz notation, we're going to look at another example of an application of the chain rule that really throws these two formulations at odds with each other. Right, so let's suppose we've got a function, we'll call it f. Let's have a look at the inverse of f. So remember, as I said before, this is not the same as 1 divided by f of x. I mean inverse in the sense of functions. So remember, if you've got a function f, then the inverse of f is defined so that this property holds, and you also need this property holding. So I think you might have covered inverse functions already, but in any case, this is how inverse functions are defined. Now the question is, if you've got a function and you found its inverse, what is the derivative of that inverse function? Well, the way we're going to find the derivative of this inverse function is by using the facts that we know. We know that this is the property that defines the inverse function. And what we're simply going to do is differentiate that. Well, the derivative of x is just 1. We know that. But how are we going to differentiate this over here? Well, we're going to differentiate this guy using the chain rule. Because this is just a composition function. It's f composed with f inverse. Differentiating then, as I said before, the derivative of x is 1. Now, to differentiate this, I'm going to use Leibniz notation because it's slightly easier on the eyes to do it that way. I said, let's have y be equal to f inverse of x. And what we're looking at doing is taking the derivative of f of y, and we're taking the derivative with respect to x. Perhaps intuitively, it makes sense what's going on here, but this notation really makes me shudder here. So in order to do this derivative, you've got to take the derivative of f with respect to y, and you've also got to take the derivative of y with respect to x. Now remember, dy on dx is actually what we're trying to find here. So all we need to do is rearrange and find that dy on dx is equal to 1 divided by df on dy. Now, as I said before, I think that this equation here is an absolute, it's a monstrosity. And so we'll try and explain what this means in the Newtonian formation. The Newtonian formation of this inverse derivative is the following. If you've got a function and you've managed to find its inverse, then the derivative of that inverse evaluated at a point x is the same as 1 divided by f prime, so the derivative of f, and you're evaluating that derivative at the point, you're not evaluating it at the point x, instead you're evaluating it at the point f inverse of x. Now this, even though maybe this is a bit, this isn't too easy to look at, it is correct. This is also correct in a sense, but you really have to do a bit of extra thinking to understand what that actually means. If you always use this formula and use it correctly, you're not going to make any errors, I hope. Right, so maybe this is a bit of a mind bender. I'd like to just pause briefly and give maybe half a minute to see if anyone wants to ask any questions. All right, I might keep moving on then. We just finished describing how to calculate the derivative of an inverse function, and now I'd like to show you an example to show how this actually goes down. And the function that we're going to apply this logic to is the function g of x, which is the natural logarithm of x. Now, just to remind you what this function looks like, well, its domain is the positive real numbers. We don't really want to take logarithms of 0, and we don't want to take the logarithm of a negative number. And it turns out that the range of this function is actually all the real numbers. Find the derivative. Well, what do we know about the logarithm of x? Well, really, I guess I haven't really defined what the logarithm of x is for you, but let me define it now. The logarithm of x is defined to be the inverse of the exponential function. So let me write that. The natural logarithm, the natural log is the inverse of the exponential function. It's this observation here that will allow us to actually compute the derivative. So with that in mind, let's define f of x to be equal to e to the power of x, so that this g of x function is actually the inverse of f inverse of x. The Newtonian formation of the chain rule tells us that, well, let's just remember what that formula said. It said this. F inverse prime of x is equal to 1 on f prime times f inverse of x. All we need to note is that f inverse is actually equal to exactly g. So if we replace this with g and this with g, we get precisely this formula here. Now remember that the exponential function is a function that has the property that the derivative of the exponential is the exponential function again. So that means that this is equal to e to the power of g of x. But remember, g of x is defined to be the logarithm of x. So what we end up with is 1 divided by e to the logarithm of x. Remember, the exponential and the logarithm functions are meant to be inverses of each other. So that means e to the power of log of x is actually exactly equal to x. And we're looking at 1 divided by x. Now, you might be tempted here to say that this derivative exists whenever x is not 0, but that's not actually true, because remember, x is not in the domain of this function here. It's the positive real numbers that are in the domain of this function. So even though this expression makes sense for negative x, the derivative does not exist if x is negative. And this is not surprising at all, because remember, the original function isn't even defined for the negative real numbers. So it's ridiculous to think that it should have a derivative where it's not even defined. So that's the derivative of the natural logarithm. Now we're coming up to another fun application of the chain rule, especially for inverse derivatives. We're looking at the derivative of the arc-sine function. So to set this up, define the function g of x to be the arc-sine function. So arc-sine is the inverse of sine. Now, you might be scratching your heads thinking, well, how can we take the inverse of the sine function? Because remember, the sine function, let's try and draw this briefly. And then we'll go up to 2 pi. The sine function looks like this. And so on. We know that in order for a function to have an inverse, it needs to be injective. And this function clearly isn't injective because it hits the same point multiple times. However, if you restrict the function to this particular range here, you find that sine is actually injective on this interval. And the range of this sine function on this interval is exactly equal to -1 up to 1. When you take an inverse function, you basically just reverse the roles of the range and the domain. So the arc-sine function has this as its domain and this as its range. So this is where the arc-sine function comes from. It's defined to be, it's a bit misleading to say it's the inverse of the sine function. Really, the correct thing to say is that the arc-sine function is the inverse of the sine function when you restrict the sine function to this particular domain there. So anyway, that's how the sine function is defined. Let's try and find its inverse. Okay, let's set up notation here. We'll define f to be sine of x so that g, which is the arc-sine function, is the inverse of f. And so remember, technically speaking, we need to insist that x is between -π/2 and π/2 for the definition of f, whereas this x is x between -1 and 1. Let's use the chain rule, or at least the results for the inverse function that we got from the chain rule. We know that the derivative of the inverse function is 1 divided by the derivative of the original function evaluated at the inverse function. Okay, so how do we do that? Well, remember, the derivative of sine is cosine. So that means this cosine goes here. But careful, we're not evaluating cosine of x, we're evaluating cosine of g of x. Because remember, g of x is equal to arc sine of x. Now, cosine. Cosine is equal to the square root of cosine squared. There's a slight technicality here, which I'll get back to in a second. Equals, now remember, the cosine squared can be written the same way as sine squared. So that means cosine of arc sine of x can be thought of as the same as the square root of 1 minus sine of the arc sine of x squared. But remember, the sine of the arc sine of x, that's just going to be x because sine and arc sine functions are inverses of each other. So in the end, what we get is that g prime of x is equal to 1 divided by the square root of 1 minus x squared. Now, question for the audience. Please answer if you can. Am I allowed to do this? Cosine equals the square root of cosine squared. What are your thoughts on that particular computation there? Yes, excellent, Zhao Wang. So the reason is, in general, I'm not allowed to do that, but I am in this particular context. So the general rule is that it is not generally true that a number is the same as the square root of its own square. It's true if that number is non-negative. Now we're looking at cosine of arc sine of x. Remember, arc sine of x lies in the range minus pi on 2 up to pi on 2. Cosine of a number that lies between minus pi on 2 and pi on 2 is actually non-negative. So that means that, yes, I am allowed to do this. So this was a consequence of the clever choice of range I selected. I can appreciate that that's not a particularly, it is a rather tricky thing to get your head around. In general, dealing with inverse functions are quite difficult, but things become a bit easier if you really focus in on what the domain and the range of your inverse functions are. Right, so that was the derivative of the inverse sine function. You can actually play these sorts of games with the inverse of the cosine and the inverse of the tan function, and you end up with these particular expressions there. The arctan function is actually defined everywhere. Its domain is all of the real numbers, and its derivative, it is differentiable for all of the real numbers. Right. Now that we've done derivatives of chain rule and the inverse functions, we'll now look at applications of derivatives. One of the neat things about the theory of differential calculus is that it actually helps us calculate limits of the kinds that we dealt with a couple of lessons ago. This very famous rule that is used a lot in mathematics is known as Lopital's rule. And the setting is as follows. You've got two functions, f and g, and we're looking at these functions close to a particular point A. What we're ultimately looking at is taking the limits of f of x divided by g of x as x approaches A. Lopital's rule says that you can evaluate that provided the derivative of the denominator is non-zero close to A, and provided both of these functions are differentiable. In that case, well, I mean, if it's true that these limits are non-zero and they're non-infinity, then you can just apply the quotient rule for limits to evaluate it. Instead, Lopital's rule concerns the special case where both limits are either 0 or they're both plus and minus infinity. This is the power of Lopital's rule, in that it tells you that in this situation, in which you wouldn't usually be able to apply the quotient rule for limits, instead you can apply Lopital's rule for limits that tells you that this limit here, the limit of the quotients, is the limit of the quotients of the derivatives, at least if this right-hand side exists. So in words, limit of quotients is limit of the quotients of the derivatives. So if you're trying to evaluate this limit, instead, you can consider this particular limit here. You differentiate the top, you differentiate the bottom, you look at that limit, and if that limit does exist, then it's going to be the same as the original limit you were interested in studying in the first place. Let's have a look at an application of this quotient rule. So we've got a comment here. indicating how easy it is to use L'Hopital's rule. Whenever I see an indeterminate form in derivatives, I end up using L'Hopital's rule. So yes, a lot of lecturers sometimes frown upon L'Hopital's rule because it is so easy to use, and it's also easy to use incorrectly. But it is a quite powerful tool that you can use, but you do need to make sure that you use it correctly. Importantly, you can only apply it if the right-hand side limit exists. Why is that so important? Well, there are examples where this limit exists, but this limit does not exist. And so if you try to use L'Hopital's rule, you might throw your hands up in the air and say, well, this limit doesn't exist because this one doesn't exist. But that is not true. These two things only coincide if this right-hand side limit exists. And there are examples where it doesn't work. So make sure when you're using this rule that you do use it correctly. As a general rule, whenever you're using a theorem, make sure that all of the conditions of the theorem are satisfied before you apply it. Now, let's have a look at an example. So this is a fun example here. We're looking at the logarithm of x divided by x minus 1, and we're taking the limit of this expression as x is approaching 1. Now, we cannot apply the quotient rule. Why is that? Well, because the bottom is going to 0, but also note that log of 1 is 0, so the top is going to 0 as well. We've got this 0 divided by 0 indeterminate form here. We can't apply the quotient rule, but maybe we can apply L'Hopital's rule. So remember, one of the conditions that you need to apply L'Hopital's rule is that both of the limits either go to 0 or they both go to plus or minus infinity. Let's see if we can apply L'Hopital's rule. Well, L'Hopital's rule says that this limit here can be found by differentiating the top. Remember, we just computed that the derivative of log is 1 on x. The derivative of the top divided by the derivative of the bottom, because of course the derivative of x minus 1 is just 1. So we've got 1 divided by x divided by 1. And this is true provided the right-hand side limit exists. Remember, at this stage, we haven't actually checked whether this limit exists yet, so we don't actually know if we can apply L'Hopital's rule just yet. But of course, you know, evaluating this limit is not an issue. It turns out that this limit does exist. It equals 1, and so that means L'Hopital's rule is applicable, telling us that this is equal to this, which is equal to 1. When you're applying L'Hopital's rule, it is good practice to include a phrase along those sorts of lines, indicating that you are aware of the fact that you can only apply L'Hopital's rule if that quotient of derivative limits you're looking at does actually exist. So do be careful with that one. I have seen, you know, exams where people will throw one of these examples at you where the L'Hopital's rule doesn't work, and some students get tripped up on that sort of computation there. Okay. One more example, and maybe we'll have another quick break. This is a fun one. We're looking at x times the logarithm of x, and we're looking at the limit as x approaches 0 from above. Because remember, the logarithm is only defined for positive numbers. It's not defined for negative numbers. So I've got a question from you, Trove. Can we provide an example where it doesn't work? Maybe I'll try and come up with an example for you during the break. I'm sure, on the other hand, if you just typed in, actually, I'm going to try this right now. I'm just going to Google situations in which L'Hopital's rule doesn't work. I'm sure I'll find something. Sorry, I just found this interesting because I do actually want to find an example now that you bring that up. So here's a sorry, I know I suggested I would look at this question, but we've got another There's one suggestion here that one situation in which this won't work is this limit here. The limits as x approaches infinity of x plus sine of x divided by x. Now, why doesn't that work? Oh yeah, okay. So what you can see, it turns out that for reasons that I won't jump into too much at the moment, this limit is actually equal to 1. And the reason for that is that you can break this up. The limits as x approaches infinity of x divided by x plus the limits as x approaches infinity of sine of x divided by x. This is obviously equal to 1, and this goes to 0 by the squeeze theorem. But if you try to do this using L'Hopital's rule, what are you going to end up with? Well, differentiate the top, differentiate the bottom, 1 plus cosine of x. This is, of course, this is just equal to 1 plus cosine of x, but we know that cosine of x is oscillating, and so this limit does not exist. So this is a situation in which the limit, the original limit does exist, but you wouldn't be able to work that out if you tried to apply L'Hopital's rule to it immediately. Hope that satisfies your desire for an example where L'Hopital's rule doesn't work. But yes, thank you for the question. That was a good suggestion. Hope that works out for you. Okay, anyway, let's go back to a situation in which L'Hopital's rule does actually work out. X times logarithm of x. A frustrating thing about this question is that you have to use L'Hopital's rule, but it's not obvious because this is not obviously a quotient. So in order to use L'Hopital's rule, we have to force this to look like a quotient. And the way we're going to do that is by noting that 1 divided by 1 divided by x is the same as just x. So we're allowed to write x times log of x like that. Now we're in a position to apply L'Hopital's rule. We differentiate the top. ln of x prime is equal to 1 on x. And 1 on x prime is equal to minus 1 on x squared, using those rules for derivatives we've already seen. Now, 1 on x divided by minus 1 on x squared. Oh, sorry. Before we get into that, it's, as I said, it's good manners to suggest to the reader that you are aware of the fact that you're only allowed to do this provided this right-hand side limit exists. I got a bit carried away then. But of course, 1 divided by x divided by minus 1 on x squared is equal to minus x squared divided by x. And if you take the limit as x approaches 0, what you end up with is exactly 0. And so that means since this limit exists, this exists, and it's equal to 0. So that is an example, another good example of the use of L'Hopital's rule. Now, I think this is probably a good place to leave it for our next break. So I'll leave it there for the moment. I'll be back in about 10 minutes, maybe a bit more than 10 minutes, we'll see. I'm hoping to get a bit of dinner in now. But yes, we'll see how we go. Please leave any questions you have or comments you have, and I'll seek to address them when I get back. All right, see you around. Hello again, everyone. Welcome to the last 50 minutes of the lecture this evening. So we just finished examples on Lopital's rule. Now we're going to come across, the next thing we're going to do is look at a very nice, interesting theorem that concerns derivatives and how they relate to averages. So remember, at the start of this session, I talked a lot about how the instantaneous rate of change was somehow a better version of the average rate of change, and that you can find the instantaneous rate of change by taking limits when you're looking at average rates of change. But it turns out that you can actually reverse this procedure somewhat. And you can do this with a very nice theorem called the mean value theorem. We have the intermediate value theorem for continuous functions, and we have the mean value theorem, which is sort of an analog of that for differentiable functions. So the theorem goes as follows. Let's suppose that you've got a function defined on a closed interval which is continuous, and let's suppose that it is differentiable on the open interval. Now, since provided all of these conditions are met, there is going to be a real number c lying in this open interval, so that the derivative of the function at that point c is the same as f of b minus f of a divided by b minus a. Now, what does this have to do with averages? Well, you know, this formula here is exactly rise on run. And another way of thinking about this is average rate of change on the interval a up to b. And so this is why this theorem is called the mean value theorem, because it tells us that the mean or the average value of a particular function on an interval is actually achieved by the derivative at some point. So the mean value theorem can colloquially, we can describe the mean value theorem as follows. The average rate of change is always going to be achieved by a derivative. It's always going to be achieved as a derivative somewhere on the interval. Now, there is a very nice graphical formulation of this particular theorem, and I went to good old Wikipedia for this particular picture. What's going on here? We've got a function f defined on an interval from a up to b. It's continuous, so it's this blue line here, which is the function f. What the mean value theorem says is that if you draw a straight line from a f of a to the point b f of b, then that straight line is going to have a particular slope. We know that the slope is the rise over run formula, which is exactly this. The mean value theorem concerns the existence of a derivative. Remember, the derivative is a tangent line. Now, the mean value theorem says that this slope here is actually going to be the slope of one of these tangent lines. If you've got two straight lines with the same slope, that means they're parallel. So that means the mean value theorem tells us that if you draw a straight line here, I guess you call it the secant, then there is a slope on this curve somewhere that runs exactly parallel to the original secant. So that's the mean value theorem. Why is it so important that we know this? Well, this, as I said before, this is a theorem that allows us to make lots of good conclusions about the original function from the derivative, because it might be the case that we don't know much about the original function, but we know a lot about its derivative. This is the theorem that allows us to work backwards and extract information about the original function from the derivative. What exactly do I mean by that? Well, this next question we've got here, I think is really, really exciting. Why do I get so excited about this? Well, in mathematics, you're quite often asked to find a solution to a problem. And that is hard enough. But then if you're also asked to show that there aren't any other solutions to the problem, that becomes really tricky. With this mean value theorem, we can actually sometimes do this. We can show that both a solution exists and there aren't any others. So let's have a look at this particular question and let's see how the mean value theorem can help us. We've got a function, f of x equals x to the fourth plus 4x plus 1. I want you to show that if we're trying to find a real number x, so that f of x equals 0, i.e. we're trying to find the roots of this function, then there are exactly 2 of them. No more, no less. Now, there's a caveat here. It tells us that we're not supposed to actually find the solutions. Why is that? Well, I think this is actually a function whose roots Mathematica can find for you. If you just chuck that function in Mathematica and ask you to find its roots, I think it will actually give them to you. But you know, sometimes it's good to not use Mathematica to do things if you can avoid it. Let's try and just show by hand that there are exactly 2 real solutions. Now, this is a fairly involved computation. It involves essentially 2 distinct parts with different techniques. And so that's how I'm going to try and format my solution to this. So, as I said, there are 2 parts, so there are going to be 2 steps. We're trying to show that there are exactly 2 real solutions. So that means that there are at least 2 real solutions. And this is what the first step asks us to show. Now, I'm hoping that you won't find this step too challenging, at least not too foreign, because the way to do step 1 we've actually already seen. We did it last time, or maybe the time before that. Show that there are at least 2 solutions. The tool we're going to use to show this is the intermediate value theorem. This is the theorem that tells us when roots exist. How do we apply the intermediate value theorem? Well, remember, we need to find points where the function is positive, points where the function is negative, and try and show, well, and the intermediate value theorem will then show that it has to cross the x-axis between those points. So really the strategy behind this first step is basically just plug in numbers to this function f until you get enough positives and negatives. So if you do a bit of mucking around, let's consider these 3 numbers: x equals -2, x equals -1, and x equals 1. If I just chuck these numbers into the function, I'll find the following, namely that at the first point the function is 9, positive. At the second point, the function is the function is -2, and at the third point, the function is 6. Okay, so we've got an interesting. Casey sent me a direct message that I think might be valuable for everyone else. Okay, so the question is, the question is about what exactly we mean by a solution. Since this is a fourth degree polynomial, Casey suggested that there should always be at least 4 roots. That's the way in which that's true. That's sort of both true and not true. So for example, consider this basic example of a function, f of x equals x to the 4th plus 1. This function here actually has no real roots. If you graph it, you see that, well, I mean, if this is x equals 0, this is positive, this is positive as well. So this function never hits the x-axis. And so now I've got a good comment from Zhao Wang. Maybe at most 4 real roots and 4 complex roots. So that's more or less, that's getting more or less close to where KC's original suggestion was. For a 4th order polynomial, there will always be 4 solutions, but in order to get those 4 solutions, you have to go to the complex numbers. And furthermore, those solutions may be identical. So yes, in general, 4th degree polynomials means there's 4 roots, but they're not always going to be real, and sometimes they might be the same. And so when I say show that it has exactly 2 real solutions, I mean, I'm not allowing myself to look at these complex solutions. And I guess maybe you're right that there is a subtlety here. When I say show that it has exactly 2 real solutions, I mean that it has exactly 2 real and distinct solutions. I want to find 2 real solutions that solve this problem that are different, and so that there aren't any others. So this is where we're going to here. So when I say step 1, show that there are at least 2 solutions, what I mean is there are at least 2, distinct solutions here. Okay, so how do we do this? Well, as I said, I found 3 points on the graph where the function goes from positive to negative and then back to positive again. So -2, -1, and then up to 1. It was at 9 here. It jumped to -2 here and then went back up to 6. Now, what you may notice is that there are a few ways I could join these dots up, but the function is continuous. So that means I have to cross the x-axis here, and then I have to cross the x-axis again here. It could be the case that this function does more than that. It could like jump up and down here, and then jump up and down here. But we're not worried about that just yet. We're just trying to show that there are at least 2 solutions. Well, the good news is, since it goes from positive to negative, and the function is continuous, remember it's good manners to check the conditions of the intermediate value theorem. The intermediate value theorem requires that the function is continuous. Since this function is continuous, I can use the intermediate value theorem to find that there has to be a root on that interval -2 up to -1. Again, the intermediate value theorem tells me that there has to be another root on the interval from -1 up to 1. So there might be, at this stage, there might be more than 2 solutions, but I've found at least 2 of them, and they're distinct. I found one root over here and another root over there. And that's more or less it for step 1. So hopefully you're now convinced that there are at least 2 solutions, 2 distinct solutions. And the techniques I've used so far are ones we have seen before. But of course, this question was asked after we introduced the mean value theorem, so there's a good chance we'll be using the mean value theorem in the next part, and that is indeed the case. Now that we have at least 2 distinct solutions, the last thing we need to do is show that this function does not have any more than 2 solutions. And this is where the beauty of the mean value theorem comes in. It more or less gives it to us immediately, but I'll try and explain these steps carefully. So as I said, we're going to be using the mean value theorem. Mean value theorem concerns differentiable functions. And so therefore, in order to use the mean value theorem, we have to compute the derivative. This is not too difficult because this is a polynomial. We just got to use the power laws. So we compute the derivative and finds that f prime of x equals 4x cubed plus 4. Now, just computing the derivative by itself is not really enough. What I want to do is notice where the derivative is positive, and I want to notice where the derivative is negative. So what you may notice is that if x is less than -1, this expression here is actually negative. So the derivative is negative if x is in this interval. On the other hand, if x is in this interval, then the derivative is positive. We've now got pretty good information about what the derivative's doing, and so we're now in a position to use the mean value theorem. Now, the way we're going to use the mean value theorem is as part of a proof by contradiction. Because remember, we're trying to show that there are no more than two solutions. And so what we're going to do is assume that we do have more than two solutions and use the mean value theorem to obtain a contradiction. So let's assume that we've got at least three solutions. We know that -1 is not a solution. So that means that there have to be two solutions on one side of -1, or there have to be two solutions on the other side of -1. So let's assume, so I'll just write out what I just said. Assume there are at least three solutions. Then, well, if I split my interval up here, -1, I know that -1 is not a solution, so I need to have either 2 here or 2 here. Then at least two solutions on this interval here, or there are two solutions on this interval here. We're now going to check these individual cases. Okay, let's assume that two of these solutions were in this interval here. If there were two solutions on that interval here, what would happen? Well, let's just think intuitively about this for a second. If there were two solutions, if there were two parts where the function f crossed the x-axis, what would have to happen? Well, if the function crossed the x-axis twice, then the mean value theorem would tell us that there has to be a point here where the derivative is 0. So let's have a look at, well, that's exactly what the mean value theorem tells us. Since f of b minus f of a divided by b minus a is equal to 0, minus 0 divided by b minus a is equal to 0, that means that there has to be a point in between these two solutions a and b where the derivative is 0. There must be a point where the derivative is 0. But we already computed the derivative, and we found that the derivative is strictly negative if x is on that interval. So that means that there can't be two solutions on this particular half of the real numbers. You can do the exact same thing on the other interval, and you can again use the mean value theorem to obtain a contradiction with the existence of two roots on the other side. So that means that there can only be one root on one half, and there can only be one root on the other half. We've already found those roots, so step 1 and step 2 combine to show that there have to be exactly two real solutions. They're distinct, there can't be any more than two, and there can't be any less than two. So this was a really fun combination of the use of the mean value theorem and the intermediate value theorem to prove that there were exactly two solutions to a problem without actually working out what those solutions were. In this example, you probably could work out explicitly what the solutions are, but really what you should be taking away from this particular computation is that this sort of thing can be applicable even if you can't solve the problem explicitly. So that's quite nice. I'll invite comments briefly. I've got a comment there. I fear might be pointing out a typo. In step 2, why is f prime positive if x is in 1 to infinity instead of x equals -1 to infinity? Yeah, that's just a typo. Thank you for pointing that out. There you go. We've got another question here. I presume this is asking about whether there's another acceptable way of doing this problem. Can I say the minima is less than 0 and f of x is convex, so there can be 2 and only 2 solutions? While that is true, later on in this particular lecture, or maybe probably not this lecture, but maybe next week, we will be looking at those sorts of things. At this stage, I wouldn't want you to say that, because we just haven't developed the machinery required. For example, we haven't defined what a convex function is yet. I'm not even sure if we will, but I mean, yeah, what you've said is correct, but at this stage, I'd say no, I'm afraid. But don't let that stop you from using that in any other context. Right, okay. So the relationship between differentiability and continuity. Last lecture, we talked about continuity. This lecture, we were talking about differentiability a lot. One question you might have already had is there a relationship between these two ideas? And the answer is yes. Differentiability is much stronger than continuity. It's possible to have a continuous function that's not differentiable, but as soon as you're differentiable, you have to be continuous. So I'll casually state this as follows: differentiability trumps continuity. If you were given a function and you were told you can have a differentiable function or you can have a continuous function, you would always say, I want a differentiable function, because that gives you more information. Differentiability is a stronger condition than continuity. And the proof of this is actually not too difficult. It's just all about definitions. Remember, differentiability means that this limit exists and is equal to a real number. So how does differentiability imply continuity? Well, let's have a look at this limit here. Remember, continuity means that f of x needs to approach f of a as x approaches a. But we're going to do this trick where we multiply top and bottom by this number x minus a. So now we're looking at the limit of a product. We're looking at the limit of this thing here times this thing here. But remember, the product rule for limits says that the limit of a product is the product of a limit. And we know that both of these limits exist. This one is just the derivative, and this one is, of course, 0. So this overall limit is equal to 0, but that's exactly the condition we want that gives us continuity. So differentiability at a point implies that the function at that point is also continuous. Now, this is part of a subsection which describes smoothness of things. We like to say that functions are smooth if they're nice and differentiable everywhere. Let's have a look at an example of a function which is continuous but not differentiable. It's not particularly smooth. Now, the example we're dealing with is this one here. The function f of x, which is equal to the absolute value of x, show that it is continuous but not differentiable. So let's just remember what this function looks like. If this is 0, this is x, and this is f of x, the function looks sort of like this. Because remember, f of x equals x if x is greater than or equal to 0, and it equals minus x if x is strictly less than 0. Now, I think last time I asked you to show that the function is continuous. I sort of did that as an exercise. It's all good if you didn't do it. I'm suggesting that it's clear that the function f is actually continuous. I think it's safe to say that the function is continuous if you're not at 0, because there you're just defined to be a polynomial, and we know those are continuous. Is f continuous at x equals 0? Well, yes. The way you can show that is by looking at left-hand and right-hand side limits, because remember last time we briefly discussed a characterization of continuity, namely that these two limits, these two one-sided limits should both exist and should be equal to whatever the function is at that point. In this case, it's 0. If x is less than 0, then the absolute value of x is exactly equal to minus x. Whereas if we're above 0, we're looking at plus x, but both of these limits are equal to 0, and this is exactly equal to f of 0. So in that sense, I think it's quite clear that the function f is continuous at x equals 0. But what about differentiability? This fails. Why does it fail? Well, remember, differentiability is defined as a limit. In order for a limit to exist, the limit has to be the same as you approach it from above, and it has to be the same as you approach it from below. So that means we need both of these one-sided limits to exist, and they both need to be the same thing. Well, let's compute them both. Let's approach this limit from above. If x is positive, then f of x is equal to x. So that's that rule there. And x minus 0, so I've got x divided by x, that's just equal to 1. However, if we're approaching from below, we use the fact that f of x is equal to minus x. Minus x divided by x is equal to minus 1. These one-sided limits both exist, but they're different. And so that means that the overall limit can't exist, which means that the derivative does not exist. Graphically, I think it's quite clear why that's the case, because remember, the derivative is meant to be describing a slope. And at this point here, we've got two different slopes. We've got one shooting that way, and we've got one shooting that way. They're different slopes, and so the function is not differentiable here. Now, I want to talk briefly about continuity, differentiability, and smoothness for multivariate functions. We won't spend too much time on this right now. I just want to give you a bit of a taste of things before we get in depth with these later on. We can talk about smoothness of multivariable functions. So here we've got a function which is strictly, it's a function of both x and y, and it's being graphed here, but technically it only really depends on x. And the function is given by 3 minus the absolute value of x. This relationship between z, x, and y is actually being graphed here. And just like the absolute value is not differentiable, this function here is not differentiable and fails to be smooth. In general, what do we actually mean when we say a function is smooth? We mean that, well, at least in the case of two variables, both the function and its two partial derivatives, they all need to exist and they all need to be continuous. Now, we haven't defined these yet, but maybe some of you know what's going on here. We say it's smooth if these are all defined and continuous. This example here is one that is not smooth. And there are lots of other fun examples of multivariable things that are continuous, but not smooth. One very important example for data science students, I would suggest, is Brownian motion. So this is motion where you have a particle that's moving quite randomly. The way in which its movement is random has some rules behind it. But the important thing is that basically all of the time, if you've got a particle moving according to Brownian motion, the movement is going to be continuous, but it is not going to be differentiable. And in fact, most of the time, Brownian motion is an example of a function which is not differentiable anywhere. So that's really interesting. We can do these sorts of things in higher dimensions. We've got fractals. Defining a fractal rigorously is quite challenging and beyond the scope of this course, I would suggest. But nevertheless, fractals are examples. Most of the time, fractals give you nice examples of things that are continuous, but they are not smooth. So that was just a brief detour into the theory of multivariable functions. We'll touch on that a bit later. Okay. Now we move on to something which is also very important for data science students, and this is the theory of optimization. Now, in fact, when I gave examples of reasons why calculus and differential calculus in particular were important at the start of this evening's lecture, I gave the example of a speedometer because it turns out that in that particular example, knowing the instantaneous rate of change was quite important. Optimization is another great example of a situation in which you need to know what the derivative is. In particular, well, we'll get to this later, but you need to know when the derivative is zero. But for the moment, we'll get to the actual optimizing a bit later, but we need some definitions before we get on with that. Okay, definition. We've got a function defined on a closed interval I. So closed interval means it looks like this. We say that this function is increasing on this closed interval if f of x1 is strictly less than f of x2, as whenever x1 and x2 are in I, and it so happens that x1 is less than x2. So what does this look like? Well, we say the function is increasing if it's going up like that, but rigorously, what does that mean? It means that if you pick any two numbers on this interval, with x1 being less than x2, then that means that the function at this point here should be less than the function at this point here. So this is rigorously what it means for a function to be increasing on an interval. Of course, you can define decreasing almost the exact same way. You pick two numbers, x1 and x2, in that order, except this time, f of x1 is bigger than f of x2. So this is what it means for a function to be increasing or decreasing. Why is it important to note this? Well, like what we saw with the example of the two roots question that we were looking at before, determining whether or not there were any more than two roots basically boiled down to computing the derivative and showing that the derivative was positive or negative. Fundamentally, the reason for that was this theorem here. We get this very nice characterization of when a function is increasing and when a function is decreasing. If the derivative is positive on the interval, then the function f is actually increasing. And this makes sense because if the derivative is positive, that means that the slope everywhere is upwards. And if the slope everywhere is going upwards, then that more or less indicates that the original function has to be going upwards as well. Same is true in reverse. If your function if your function's derivative is negative, then f is decreasing. This is another fun one here. If you have a function whose derivative is zero everywhere, then f actually has to be constant. So that's quite nice. So let's have a look at proving this. This is basically just a consequence of the mean value theorem. So how does this work? In order to show, let's try and prove the first one. To show that f is increasing, we need to take x1 and x2 that are in that interval. We need to show that f of x1 is less than f of x2. And we need to show that's true for any x1 and x2 that are in this interval with x1 less than x2. What I'm going to do is apply the mean value theorem to this interval here. What happens if I do that? Well, the mean value theorem tells us that the difference of these two, the function evaluated at these 2 points divided by x2 minus x1, that has to actually be achieved as a derivative somewhere. What is so great about this? Well, depending on which of these situations we're in, we get this great information about the derivative. So in particular, if we're trying to prove the first one, if we're assuming that f prime is positive, then that means that this thing is positive. Since x2 minus x1 is positive, I've got a ratio of 2 things here, and it's positive. Since the denominator is positive, that means that the numerator has to be positive as well. And this means that f of x2 is actually bigger than f of x1. Since this is true for an arbitrary pair of numbers x1 and x2 in that interval, that means that item number 1 is true. Great. Now, the proof of the others is essentially the same. So for example, if the derivative is negative, then you get this. If the denominator, this time the denominator is still positive. So if the numerator divided by the denominator is negative and the denominator is negative is positive as well, that means that the numerator has to be negative. So we have to be decreasing. On the other hand, if this thing is exactly equal to 0, then that implies that f of x2 has to equal f of x1. This is true for any x1 and x2, and that means that the function has to be constant. So this is a great application of the mean value theorem here. Intuitively, perhaps it's quite obvious, but the mean value theorem turns out to be one of those theorems that allows you to make your intuition rigorous. So question finds the intervals on which f of x, which is defined to be x cubed plus x, is increasing or decreasing. Well, this function f of x is differentiable everywhere, so that means there's a good chance we'll be able to use that theorem just before to work out whether or not this function is increasing or decreasing. Well, the derivative of this function is x squared plus 1. X squared is always greater than or equal to 0, and 1 is certainly bigger than 0. And so that means that this function f is increasing, and in fact it's increasing everywhere. It's increasing on the interval r. Now I know technically speaking we only defined increasing and decreasing on closed intervals, but r, even though it's defined to be the interval from minus infinity up to plus infinity, it turns out that it's both closed and open. So we can think of this r as both a closed and an open interval. In fact, sometimes you call this clopen. R is a clopen interval. Just as a fun fact for you, by convention, the only intervals in R that are both open and closed are the empty set and the whole set of real numbers itself. So that was just a fun fact for you. Now we'll get on to the actual optimization. Definition, local extrema. So when I say extrema, I mean maximums and minimums. So when I say local extrema, I mean local maximums and local minimums. If you've got a function f, then you say it has a local maximum at a particular point A. If you can find an open interval I containing that point A, so that f of A is greater than or equal to x for all x in that open interval, we also need to insist, obviously, that x is in the domain of f. On the other hand, a local minimum at a point A occurs if f of A is less than or equal to f of x for all x in that interval intersected with the domain of f. This was local. We can also talk about this globally as well. Globally just means we drop the reference to this particular open interval I. So a function f having a global maximum at a particular point A that means that f of a is greater than or equal to f of x for all x in your domain. On the other hand, of course, a global minimum means that f of a is less than or equal to f of x for all x in your domain. Maybe this is obvious, but probably worth mentioning that any global maximum is going to be a local maximum, and any global minimum is going to be a local minimum as well. Now, in the quest for finding global maximums and minimums, well, first let's think about why it would be useful to know about maximums and minimums. 9 times out of 10, the reason for this is going to be money. You've got a particular function that describes the state of a particular situation, and you want to find the inputs that maximizes the profit. So this is more or less where optimization comes from. Mathematicians that are employed in industry, 9 times out of 10, what their job entirely revolves around trying to save their company money. Okay. Now, in the quest to find such maximums and minimums, it turns out to be useful to describe the notion of a critical point. So I know this is all a bit abstract at the moment, but trust me, soon we'll explain why we're making all of these definitions. We say that a function f has a critical point at a particular point in its domain if one of two things happens. Either the derivative is 0, or f prime of a does not exist. So that's how we define a critical point. What do critical points look like? Well, there are a whole bunch of reasons why a point may be a critical point. So I took this image from the workbook here, the course reader. Figure 50, what do the points P, Q, R, S, T, and U all represent? Of course, the answer is they are all critical points. But now my question to you is why? Why are all these points critical points? So maybe I'll get some input from the chat here. Let's go through this one at a time. Let's start with a tricky one. Why is P a critical point? This probably is P and U are probably the trickiest of all of them. Why is P a critical point? Yes, so I've got the answer from Zhao Wang here. There are no left limits, because remember, in order for the derivative to exist, we need this limit to exist. And for a limit to exist, it needs to exist from both the left and the right-hand sides. Now, we haven't defined this function over here. And so that means, even though it's unfair, we have to say that the derivative at this particular point does not exist just because it fails to be defined left of the graph. Because f prime of P does not exist. And the same goes for U as well. All right, so those were perhaps the toughest ones. We've got 4 other points to deal with. Q, R, S, and T. At Q, S, and T, the slope is 0. So yes, thanks for that seminar. Slope is 0 at Q, S, and T. What about this point R? At R, the derivative does not exist. And this is sort of for the same reason we saw before. We've got two different slopes here. And for a derivative to exist, the slope needs to coincide there. So that's hopefully that gives you an idea of critical points here. Now, before moving on, maybe I'll ask one more question before we wrap up. Based on this definition of critical points, what does critical points have to do with finding maximums and minimums? Who can cleanly describe what the relationship between local extrema, global extrema, and critical points are? Yeah, thanks for that, Zhao Wang. That's more or less correct. They can be local extrema. Yes, that's another good answer. They can be local extrema. Good, thanks for your responses, everyone. The precise relationship is as follows. It's said rigorously in this theorem here. If you've got a local minimum or maximum of f, then A is actually a critical point of your function there. Now, I'm going to state this a bit more casually for you. All local and global extrema are critical points. But not all critical points are extrema. So I've got a question here. Is a point of inflection a critical point? Well, I'm going to give a typical mathematician response here and say it depends on your definition of inflection point. I think the definition of inflection point I'm thinking of is when I've seen definitions of critical points. It really depends on your definition of an inflection point. So, for example, sometimes all you need for a point of inflection is the second derivative to travel from I can't remember how it's defined, but there are versions of inflection points that are classified as critical points and some that are not. Okay, so I've got a suggestion here that in generally the answer should be no. So I guess in that particular case, I mean, if you're thinking of if you're thinking it like, I think the definition of inflection point is where convexity turns into concavity. So that's when the second derivative changes from being positive to negative. And if that's your definition of inflection point, then no, it's not necessarily the case that all inflection points are critical points, but it really depends on your definition. Okay, I'm trying to decide whether or not to do this proof before we finish. Yeah, I think we'll give it a go. Maybe we'll do it quickly and we'll quickly review it next time. Let's suppose that you've got a local maximum. Then by definition, what that means is that f of a is actually bigger than or equal to f of x for all x that are sufficiently close to a. Okay. Now, if the derivative doesn't exist, then we're done. Because if the derivative does not exist, then we're necessarily a critical point, and great. But what happens if the derivative does exist? Well, remember, for a derivative to exist, that means that a certain limit has to exist. And that means that the limit has to exist when you travel to it from either side. Both the limit from above needs to exist, and it has to be the same as the limit from below. Now, if x is less than a, then x minus a is negative. But remember, f of x is less than or equal to f of a. So f of x minus f of a, I've done this wrong. Wait. I think maybe this is supposed to be a positive here. If f of x minus, if a is a local maximum, then the top is negative and the bottom is negative if we're traveling to a from below. So it's going to be greater than or equal to 0, I think. On the other hand, if you travel to it from the other way around, you'll get this less than or equal to 0. You've got the left-hand limit, which has one sign, and the other limit, which has the other sign. And for the overall limit to exist, those two limits both have to coincide. But the only non-negative number that's also non-positive is 0. So that means the derivative is 0, and we have a critical point as required. All right, that's a good place to stop. I'll leave it there. Thanks for your attention. Okay, I've got a comment suggesting that my original slides were correct. Fair enough. I'll review that and make sure it's good for next time. Thanks for your comments, everyone. I'll stop recording there. See you next time.